What makes irrational numbers infinite and non-repeating in algebra? Have you ever wondered why some numbers just go on forever without repeating? Today, we are going to look at irrational numbers and discover what makes them infinite and non-repeating in the world of algebra. To start, let's clarify what irrational numbers are. These are numbers that cannot be expressed as a fraction of two integers. This means you cannot write them as a simple ratio, which is a key reason why their decimal expansions go on forever without forming a repeating pattern. We know that real numbers are made up of rational and irrational numbers. That is why irrational numbers are important, because they make the set of real numbers continuous by filling in the gaps between rational numbers on the number line. Now, let's compare this with rational numbers. Rational numbers can be written as a ratio where both the numerator and denominator are integers and the denominator is not zero. For example, 1 over 4 can be written as 0.25, which is a terminating decimal, meaning the decimal expansion ends. In this case, it ends at 5. Another example is 1/3, which can be expressed as 0.3 repeating. Irrational numbers, however, do not fit this mold. Their decimal expansions neither terminate nor repeat. You can keep calculating more digits, but you will never find a finite endpoint or a recurring sequence. A major source of irrational numbers comes from square roots. Specifically, when you take the square root of a number that is not a perfect square, the result is always irrational. Remember, perfect squares are numbers like 1, 4, 9, and so on. Let's look at our first concrete example, the square root of 2. If we try to write this as a decimal, we get 1.414213 and so on. Notice how the digits go on forever and there is no clear repeating pattern. Because there's no pattern, we cannot write it as a simple fraction, confirming it is irrational. Here is another quick example, the square root of 3. Like square root of 2, the digits continue infinitely without ever settling into a repeating sequence. These examples show us that while some square roots are rational, like square root of 9, square root of 25, many others are not. We just saw that roots of non-perfect squares are irrational. Now we move to a set of numbers that are even more fundamentally irrational. They are called transcendental numbers. Transcendental numbers are irrational numbers that are not the root of any simple polynomial equation with whole number coefficients. The two most famous irrational numbers are pi and Euler's number. First, we have pi, symbolized by the Greek letter. Pi is defined as the ratio of a circle's circumference to its diameter. No matter how big or small the circle is, the ratio is always pi. Since we cannot express it as a simple fraction, its decimal representation goes on forever without ever falling into a repeating pattern. The second famous number is Euler's number, symbolized by E. Euler's number is critically important, especially in areas dealing with continuous growth like compound interest or population dynamics. If you look closely at the first few digits after the decimal points, you might see the pattern starting to emerge. 718281828. However, while these digits appear close together, the pattern does not continue indefinitely. If it repeated forever, it would be rational. Because it doesn't, Euler's number remains firmly in the irrational family. So, how do mathematicians know these numbers are irrational? We use a powerful technique called proof by contradiction, where we try to show that assuming the opposite leads to an impossible situation. First, we assume the opposite. We start by assuming the number we are testing is rational. If we are testing square root of 2, we assume it can be written as a simple fraction p over q. Crucially, we state this fraction is in its lowest terms, meaning p and q have no common factors other than 1. Next, we use logic or math. We then manipulate this assumption using algebra. If our assumption is true, the resulting equations must also be true. We perform these calculations hoping to find a problem. Lastly is the conclusion. If our logical steps lead to an impossible statement, a contradiction, then our initial assumption must be false. If assuming the number is rational leads to a lie, then the number must be irrational. This is how we gain certainty. Now, let's see the proof of contradiction using square root of 2. First, we assume the opposite. We assume the square root of 2 is rational and can be written as p over q in the lowest terms. Next, we square both sides. This equation p squared equals to 2q squared tells us that p squared is an even number because it is 2 times another number q squared. If p squared is even, then p itself must be even. We can write p as 2k, where k is some integer. Now, we substitute p equals to 2k back into the equation. We get 4k squared equals to 2q squared. Dividing both sides by 2 gives us q squared equals to 2k squared. This new equation shows that q squared is also an even number. If q squared is even, then q must also be even. We have proven that p is even and q is even. This means both p and q are divisible by 2. This contradicts our initial assumption that p over q was in its simplest form and shared no common factors. Since the starting assumption leads to this logical breakdown, the assumption is false. Therefore, we conclude that square root of 2 is irrational. To wrap up our discussion on infinite decimal representations, let's review the main difference between the two types of numbers we've discussed: rational and irrational. Rational numbers can be always written as a fraction p over q, where p and q are integers and q is not 0. Their decimal forms are orderly. They either terminate or they repeat a sequence forever. Irrational numbers, on the other hand, cannot be expressed as a fraction of two integers. Their decimals are chaotic. They are infinite and non-repeating. Think of square root of 2 or pi. The key idea is that irrational numbers are necessary to completely fill the number line. They represent values that cannot be perfectly captured by simple division. Understanding this difference is crucial for working with geometry, calculus, and advanced algebra. Thank you for listening.